let us proceed from what we have left over from our previous videos. For now, we have acquired the AS required, and this AS required is generated on basis of the assumed value of the KR. Previously, we assumed the KR because we do not have the AS. Now we have the AS. We're going to go back and get the actual KR. See if the assumed value is the same as the AS provided. It is only when the KR is the same as the assumed, then the calculated AS required, it will be valid. If the KR is not the same, then you will have to continuously acquire the AS and test the KR again until the KR is more or less constant. In these videos, we're going to discuss about this. Now, based on the experience of our previous example, dealing with the brace and slender column, we come to a state that the proposed amount of reinforcement bar fails the maximum bar area. Knowing that the maximum bar area would have failed, actually the following calculation step, it will be meaningless. To avoid unnecessary works to be done, maybe let us first check the amount of reinforcement bar against the maximum and minimum rebar requirements. Since we have the initial AS required of 101638, we're going to propose 6H20. The AS provided, it will be 1885 mm squared, which is larger than the AS required. Then it is acceptable. Now we're going to check for the AS min and the AS max. Equations for the AS min is given here. 0.1 times MED divided by 0.87 times FYK. MED is given 147.36 kN. FYK also given 500. That leads to you 34 mm squared. And then we look at 0.2% of the cross-sectional area of the column. AC here is calculated as 175 times 300 times 0.2%. You need 105 mm squared. The AS min shall be the greater of the two value, which is 105 mm squared. Compared with the AS provided, the AS provided is actually greater than the AS min. That means it passed the AS min requirement. How about the AS max? You're going to take the AS provided, 1885, divided by the cross-sectional area of the column, which is 175 times 300. Your reinforcement bar ratio, it will be 0.036. That means it is less than 4% of the cross-sectional area of the column, which is acceptable. At the lapping regions, the amount of reinforcement bar double, and it is less than 8%. So it is also acceptable. This gives us an idea that you do not need to enlarge this section, and you may proceed with the following calculations. And probably let us do with the shear link first. These are the requirements for the link. Minimum bar size 6 mm, and it should be at least a quarter of the maximum bar provided. The longitudinal bar diameter is 20. 1/4 is 5 mm. The bigger values is taken. That means your minimum size of the link will be 6 mm. And then we determine the maximum spacing. It is governed by 4 factors here. Not more than 400 mm. Not larger than the dimensions of the column. The B is 175, the H is 300. And also not exceeding 20 times the longitudinal bar size, which in this case 20 mm is provided. 20 times 20, that gives you 400. We will use the smallest value of all, That means now the S maximum, it will be 175. Your maximum spacing is 175 throughout the column. However, at the lapping regions, when the bar diameter is more than 14 mm, as well as at the locations or hedge distance above and below the beam, where the joints of the column, the maximum spacing will have to reduce for 40%. Therefore, you will use this 175 times 0.6, you get 105. Now, based on these requirements, you may provide R6 150 for the column, whereas at the joint regions or at the lapping regions, you can provide R6 100. Now, having the reinforcement bar requirements checked, as well as having the shear links confirmed, we will come back to deal with the AS required. We haven't confirmed the KR. Now we have the AS required. We're going to substitute into the equations and generate the calculated KR. This is what we are going to do. We need to generate the omega, which is in the functions of AS multiply the design yield strength of the steel bar, divided by the cross-sectional area of the column multiplied with the design strength of the concrete. This omega represents the axial capacity of the steel bars against the concrete section. Now we have the AS. We also have the FYD. We have calculated it previously, equals to 435. We also know the cross-sectional area of the column, 175 times 300. Now we need to calculate FCD, which is given in the formula here. 0.85, it will be the factors correlating the compressive strength with the flexural compression strength. 0.85 times FCK, 30 Newton per mm square, divided by partial factor of safety of the concrete, which is 1.5. That gives you FCD equals to 17. Substitute the relevant value, you get your omega equals to 0.798. Substitute the omega into the equations, you get NU, which is 1.798. And then you need to calculate the N. The N is a ratio representing the percentage of the concrete capacity of the column taken by the load. You have the NED, 147.36 kN, divided by AC FCD, 175 times 300, and FCD equals to 17. That gives you an N equals to 0.165. And then you have N balance, you assume it equals to 0.4. Substitute those values into the equations, you get KR equals to 1.168. This KR needs to be less or equals to 1.0. The calculated value is more than 1.0. Then we will use KR equals to 1.0. Now you found that the calculated KR here agrees with what we have assumed previously, which is also KR equals to 1.0. What does it mean? It means that no modifications to the curvature 1 per R, no modifications to the eccentricity E2, and no modifications to M2. Because of that, there won't be any modifications to the subsequent steps, such as calculating the MED for the slender and unbraced column. And there also won't be any modifications due to the biaxial bending, which you do not need to recalculate the MED prime Y, and you can use this 42.1 kN meter safely. Now, when the design load is the same, That means the calculated AS shall also be the same. Now initial proposed reinforcement bar 6H20, it would be sufficient. With that, you're going to stick with the same arrangements of the reinforcement. 6H20 in the minor axis. Since in our previous calculation steps, we know that the minor axis, it will be more critical. Also in our previous calculation step, we know that we cannot ignore the biaxial bending. That means we have to go through a check for the biaxial bending. In the calculations of the biaxial bending check, now we have to look separately for the major and the minor axis. We are looking into the ratio between the moment acting in the axis divided by the moment capacity as provided by the provided reinforcement bar. Therefore, the arrangement of the reinforcement bar, it will be important. You need to identify the effective reinforcement bar with respect to both axes. With the provided amount of reinforcement bar 6H20, this shall be the layout. You will have effective 6H20 in the minor axis. However, two of the reinforcement bar falls in the neutral axis of the major axis. That means these two reinforcement bar is not functional in resisting moment in the major axis. Effectively, the amount of reinforcement bar in the major axis, you cannot take it as 6H20. Instead, it will be 4H20. With that, you will generate the AS provided for the major and the minor axis. They are not the same. Having this understood, we will need to generate the moment resistance of the column in the major and in the minor axis based on the effective reinforcement bar provided. By doing so, we're going to use the design chart again. First, we need to determine which design chart to be used. Find the D2 per H ratio first for both the major and the minor axis. D2, it will be the concrete cover 35 mm plus the size of the shear link 6 mm plus the size of the reinforcement bar divided by 2. That means 20 mm divided by 2. That gives you D2 equals to 51, which we have calculated previously, divided by H. In the major axis, the H is 300. As in the minor axis, the H, it will be 175. That gives you D2 per H ratio of 0.17 and 0.291. Use the column chart of 0.15 and 0.25. Then you're going to generate numbers in the y-axis as calculated from NED, which is 147.36, divided by BH 175 times 300, and divided by FCK 30 Newton per mm square. Your y-axis value, it will be equals to 0.094. And then you need to generate the value for AS FYK per BH FCK. With the AS provided times FYK 500 divided by BH 175 times 300 and divided by FCK 30 Newton per mm square. That gives you 0.399 and 0.598. Based on the value acquired, we're going to adopt them in the design chart. First, let us deal with the major axis. Use the design chart. D2 per H ratio equals to 0.15. Draw a horizontal line at 0.094, and then for the AS FYK per BH FCK, we are looking at the curves. We want the curve of 0.399. That means we're going to trace along the curve of 0.4. This will be the intersection. Draw a straight line down to the x-axis. It gives you the value of the x-axis equals to 0.157. That means m per bh square FCK shall be equals to 0.157. It will do the same for the minor axis. Minor axis will use the chart of 0.25. Draw a horizontal line for 0.094. Find the AS FYK per BH FCK equals to 0.598. That means you are referring to the curve of 0.6. The intercept here. Draw a straight line downward. It falls somewhere at 0.17. That means for the minor axis, the m per bh square FCK is equals to 0.17. Based on this, you can calculate the moment resistance of the reinforcement. Get the MRD from the major axis by having the 0.157 multiplies the B and H square and FCK. In the major axis, the B it will be 175, the H it will be 300 square, and FCK equals to 30. That gives you the moment resistance of 74.2 kN meter. And then get the moment resistance in the minor axis. 0.17 multiply BH square FCK. Since we are dealing with the minor axis, that means the H is now 175. You are talking about 0.17 times 300 times 175 square times FCK. Your moment resistance is 46.9 kN meter. For now, we have acquired the MRDZ and also MRDY. The following step, it will be for us to determine dA, which is obtained from the table here through interpolations with reference to the percentage capacity ratio, NED per NRD. And then later we're going to determine the moment acting onto both axes. Only when we acquire all those values, we're going to check holding here not exceeding 1.0. If the value exceeds 1.0, that means we need to repropose the layout of the reinforcement. Most likely we need to increase the reinforcement, either to increase the moment resistance in the major or in the minor axis. If the whole thing here is less than 1.0, that means the proposed amount of reinforcement is adequate. Then you can finalize the amount of reinforcement. Due to the length of the video, maybe we stop here and we shall proceed with the following calculations in the following videos.